Hello and welcome, brothers and sisters. I am your host, your brother, your professor, Mr. O'Neill Barnaby, founder and director of the Black Math Academy, here trying to rebuild intelligent black society through mathematics. Today, I'm going to be talking about a concept called imaginary numbers. In a previous video, I discussed number theory, and one of the categories was called complex numbers, and that's where imaginary numbers actually came through. So I mentioned it briefly in that video, but today I'm going to go a bit in depth as to what are imaginary numbers. Because here at the Black Math Academy, we don't just tell you what something is, we also tell you why something is. So let's see how deep this rabbit hole goes. So in order to talk about what imaginary numbers are, I need to first discuss what square rooting is, because that's where imaginary numbers comes from. So we'll start with problem, the square root of 25. All right, so what square rooting is that you're trying to find some number that when you multiply it by itself gives you the value inside the radical or the symbol. So this 25 here. So some number that when you multiply it twice gives you 25. So one answer that comes about from this is the value 5. So why 5? The reason being is because 5 times 5 is 25. So it just makes sense. But what's interesting about square root problems is that there's actually two answers to every square root problem. There's a positive version and a negative version of that answer. So positive 5 isn't actually the only answer. There's also negative 5. Because negative 5 times negative 5 is also 25. So 5 and negative 5 would both be answers to the square root of 25. But let's say you're trying to take the square root of a negative number. So let's say the square root of negative 25. Well, by definition of square rooting, this problem is impossible. There's no way to find a number that when you multiply it by itself gives you a negative answer. Because as we can see, two positives, 5 times 5, gives you another positive answer. And two negatives, negative times negative, also gives you a positive answer. So there's no way to take some number that when you multiply it by itself gives you a negative answer. So it's impossible. However, there was this dude named Leonard Euler way back in the day, generations ago, who said, well, what if you could? Let's just say there was an answer to a problem like that. Well, what would it be? He decided to call it I as in imaginary numbers. So what he did was start with a small negative number, and he said, well, let's start with the square root of negative 1, and the answer to a problem like that, I'm going to call it I. So in mathematics, the square root of negative 1 is called I. Well, what's cool about mathematics is that what we can do is use previous knowledge and information about mathematics to discover something new about mathematics. So based on this rule here, we can then apply all the rules of algebra to discover something new. For example, let's say in this particular equation, let's say we wanted to take both sides to the second power. So this side squared and this side squared. Well, algebra dictates I can do that because algebra says what you do to one side of the equation, you have to do to the other side of the equation. So I can take both sides to the second power. No problem there. So let's see what happens. Well, I squared is exactly that. I squared. So nothing changes there. But on this side, the square root of negative 1 squared, because squaring and square rooting are inverse operations of each other, they actually cancel out. So the 2, or the power, and the square root symbol actually disappear, and -1 remains. So -1 would be the result. So we just discovered that when you square I, the answer is -1. So based on one rule, we were able to figure out something new. So I'm going to show you a few of those rules here. So first we said that I was equal to the square root of -1. And when we squared both sides, we just discovered that I squared is equal to -1. All right. And based on this information, I can actually keep going. There are more things to learn about imaginary numbers. So let me erase this real quick. And let's say that you wanted to find out the value of I cubed. Okay. So again, like algebra, we could use what we've already learned about mathematics to find out something new. So I cubed can be a little weird to handle with, but we do know that if you take I squared and multiply it by I, that equals I cubed. From the rule, when you're working with exponents, when you multiply powers with the same base, you actually add their powers. So this 2, and for this I, there's an imaginary 1 sitting above it. So because they both have the same base and you're multiplying these two values, we add their powers. So 2 plus 1 becomes 3. So I squared times I is I cubed. Luckily, we know exactly what I squared and I are. I squared, we know, is -1, and I is the square root of -1, but I is also equal to itself. So I is I. So we can say from here that -1 times I would be the answer. So -1 times I is -I. So I cubed would be equal to -I. You see what I'm saying? And we can go even further. Let's say you wanted to find out the value of I to the 4th. Right? So we'll use the same tricks that we did before. I to the 4th can be rewritten as the value, or the expression I squared times I squared. Again, multiplying powers with the same base, we add their powers. So I squared times I squared will be add their powers, so 2 plus 2. And this problem ends up resulting in I to the 4th. And since we know exactly what I squared is -1, what this is really saying is -1 times -1. And -1 times -1 is 1. So now we've just figured out exactly what I to the 4th is. I to the 4th is equal to 1. And what actually ends up occurring is that these 4 values, I squared, I cubed, and I to the 4th, actually repeat themselves. They become cyclical at this point, and allow me to show you how. Let's say you wanted to find out what I to the 5th was. All right, so again, we'll use what we know previously. I to the 5th can be rewritten as I to the 4th times I. Because multiplying powers with the same base, you add their powers. So there's imaginary 1 sitting up here, so it'll be 4 plus 1 in the end. And this will be I to the 5th as a result. And once again, we know what I to the 4th is, and we know what I is. I to the 4th is 1. I is just I. So this would say 1 times I. And 1 times I is just I. Anything times 1 is itself. So I to the 5th is I. And since I is equal to the square root of negative 1, it also equals that as well. So it went right back to where we started. And a neat way to kind of remember those values is that as long as you keep adding 4 to the original powers, all the answers are going to be the same exact value. So I is like saying I to the 1st. And 1 plus 4 is 5, which gives you the same answer. 2 plus 4 is 6, so I to the 6th would be the same as this one, negative 1. 3 plus 4 is 7, so I to the 7th would be also negative I. And I to the 4th, if you add 4 to that, it'll be I to the 8th. And I to the 8th is also equal to 1. So all those answers just keep repeating themselves over and over again. So there's no real need to remember all those extra values. As long as you know the first 4, you'll be in pretty good shape. Right? So where are imaginary numbers useful? Because they don't really make much sense in as you're thinking about it. Well, imaginary numbers are useful when it comes to electricity, specifically when it comes to alternating current or AC current, because when you're trying to put those currents together, they get very difficult because it goes from positive to negative as you go through the system. So complex numbers or imaginary numbers actually makes the combining of those currents easier, which is helpful because when you combine them, you want to make sure you don't electrocute yourself. So that's how that's helpful. Duh. It also is helpful where those displays when it comes to sound, like on radios, when the bass or the treble is playing and those bars go up as the sound is playing, that's also an aspect of complex numbers or imaginary numbers. And also when it comes to filtering out sounds, so in a large crowd, like in a concert, you have people screaming and maybe you have a few people here and there conversing with one another in a lower level. Complex numbers or imaginary numbers also filters out the crowd so you can pinpoint just the people who are whispering or just having a casual conversation with each other. So it's also helpful in that regard. So imaginary numbers is helpful in more places than you think. All right. So that's another example of intelligent Black society. The Black Math Academy is here being clear, being concise, and being articulate, which is why we are without peer. Don't forget to like, share, comment, and subscribe to all of our social media platforms, our Facebook page, Instagram page, and YouTube page. And always remember that we reap what we sow, but are you prepared for the harvest?